And so you can see that here, that we've got these different sequences, A, B, and C, and B is trapped in between A and C everywhere. And A and C both go to the same limit there. And so therefore B must also as well, because it's in between them like that. So even though B isn't behaving nicely and it's bouncing all over the place, A and C are easier to do, and therefore we can figure out what it is. All right, so let's try one right here. So we have cosine n over n. Will you just pull that out of the door so we don't have to listen? Thank you. It's gone. I don't know. All right. So if we look at this, cosine n over n goes to 0. Okay, we want to show that that is what it converges to. Okay, so we're basically having the answer and we're going to show it. So what we need is some sequences that are always smaller than it and always larger than it. All right. And so a good way to do this, remember cosine of n, or at least greater than or equal to it. Cosine n is always going to be something that has a magnitude less than 1, right? So we can say then that cosine of n over n is always going to be less than or equal to 1 over n. We agree with that? Because that cosine n numerator is always 1 or less, right? So therefore, it's going to always be less than that one. And since we're saying this goes to 0, we need something basically, so this 1 over n is going to come down and can sandwich us from the top, but what about from the bottom? Anybody want to venture a guess on that? Yeah. So we can also do this, -1 over n. And so it's sandwiched in between those. And since we know the limit as n goes to infinity of plus or minus 1 over n is 0, therefore cosine n over n also goes to 0. Okay. So what about this one? What about this next one? Can we think of something we can sandwich in between here, some sequences? Yeah, we don't have to actually do necessarily that one. We can do one of them the same. You can do 1 over 2 to the n less than or equal to 1 over n. That works. But what about on this other side? What can we do? We can go much simpler. It's always greater than 0, right? There's nothing we can put in that exponent. There's nothing we can put in for n that's going to give us a number less than 0. So it's always greater than 0 and less than or equal to 1 over n. Now we couldn't do that with the one right before it because cosine, positive, negative. So we have to stay below there. But with this one we can do that. And 0 goes to 0. 1 over n goes to 0. Therefore, 1 over 2 to the n goes to 0. Making sense? Okay. Any questions? No? Okay. Let's go with the continuous function theorem. I think I was going to go to, hold on, I'm trying to check. I had decided where I was going to stop. Yeah, just a couple more pages, then we'll stop and y'all can work on these because I feel like this is a little bit heavy, so not rushing through it here. So continuous function theorem. So let's say we have our sequence AN, and it be a sequence of real numbers. If AN goes to L, so our limit of it goes to L, or converges to L, and if F is a function that is continuous at L and defined for all the A sub n's, then F of A sub n will also go to F of L. Great, what's that good for? Well, let's take a look here. We want to show that the square root of n plus 1 over n goes to 1. So what we're going to do is we're going to let f of x equal the square root of x. Okay? That's what we're going to make be our function. So now we can look and say, if n plus 1 over n goes to 1, then f of n plus 1 over n goes to f of 1. So what we really want to do is we want to show this, and we want to then do this. All right? So let's show it. Let's do limit as n goes to infinity of n plus 1 over n. So how can I do this limit? What was that? Well, you just always want to go to that, don't you? Yeah. I just split it. I'd say, all right, this is the limit as n goes to infinity of n over n is 1 plus 1 over n. That's what that becomes, right? 1 plus 1 over n. And then that's really easy. So we end up with 1 plus 0, 1. All right, so we showed that. And then therefore, f of n plus 1 over n goes to f of 1, which means f of n plus 1 over n is square root of n plus 1 over n, which is what we were looking for. And therefore, it goes to square root of 1, which is just 1. We're using the behavior of a function to determine what this is doing, right? Okay. So let's take a look at this next one. Show that 2 to the 1 over n goes to 1. So what function do I want to use here? Nope. Use more of the outer thing. Ooh, where are you getting that? So up here, we had square root of, and then something crazy inside the square root. So we just made the function square root. There you go. What did you say? 2 to the x. There you go. Okay. So we need to look at the limit of what our x is there, right? Which is the 1 over n. So limit as n goes to infinity, as n goes to infinity of 1 over n equals, and what is that? 0. Therefore, f of 1 over n right? And so 2 to the 1 over n goes to 2 to the 0, right? Which is 2 to the 1 over n going to 1. Pretty cool. Doesn't seem entirely groundbreaking, right? We're just taking the limit of what's ever inside of our function and then just applying the function to it, right? But it works. All right, any questions on that? And for Alejandro. Huh? All right, the following theorem allows us to view, what? What happened? Okay. The following theorem allows us to view sequences as a function, allows us to consider sequences and functions when evaluating the limit. So suppose that f of x is a function defined for all x greater than n naught, and that the sequence a sub n is a sequence of real numbers such that a sub n equals f of n for all n greater than n naught. Then what we're saying is the limit of our sequence is L whenever the limit of the function is L. Okay, so let's take a look at this. So therefore, we may differentiate to apply Hopital's rule, but remember to check that the limit is in an indeterminate form, which is our 0 over 0, our infinity over infinity, or our infinity times 0 first. Okay, etc., etc. All right, does the sequence whose nth term is a sub n equals the quantity n plus 1 over n minus 1 to the n converge? If so, let's figure out what. Ooh, who do we lose? So let's see if this converges. So we need limit as n goes to infinity, n plus 1 over n minus 1 to the n. Okay. And that is going to become what? 1 to the infinity. And so that's not good, because for Hopital, what do we need? No, what I mean is, well, I guess, but we need an f of x over g of x kind of a thing, right? Which we don't have here. So let's do some trickery to get it into something like that. So limit as n goes to infinity. We're going to make this e to the ln of n plus 1 over n minus 1 to the n. Right? We can do that because e to the ln of x is x, right? They undo each other. But what this allows us to do is make this limit as n goes to infinity of e to the n times ln of n plus 1 over n minus 1. See that? So now we don't have that exponent up there anymore. And so here what we can do then at this point is we can let f of x equal e to the x. And then what we need to look at is the limit as n goes to infinity of just n times the natural log of n plus 1 over n minus 1, which I can then rewrite as limit equals of n goes to infinity of natural log of n plus 1 over n minus 1 over 1 over n. And now we can use Hopital. So we go up here for this numerator part. We can do the derivative. So natural log of natural log n plus 1 over n minus 1. What's that derivative going to be? Yeah. We got to do chain ruling, right? Right. So we do the derivative of the outer. So that's 1 over n plus 1 over n minus 1, right? Times the derivative of what's on the inside. And the derivative of what's on the inside is a quotient rule, right? So we do the derivative of what's on top, which is going to be just 1, times what's on the bottom, minus the derivative of what's on the bottom times what's on the top. And the derivative of what's on the bottom is -1, or just 1, sorry. I saw that -1 and threw it out there. So it'll be n plus 1 times 1 all over our denominator squared, right? Remember doing that? And then you start in on your algebra and you end up with n minus 1 over n plus 1 times, what do we have here? N minus 1 minus n plus 1. So that's what? N minus 1 minus n minus 1. So that should give us an -2 over n minus 1 squared. We have an n minus 1 over an n minus 1 squared, right? So that's going to cancel with that. And we have -2 over n plus 1 times n minus 1, which is -2 over n squared minus 1. Okay? Then for the denominator part, we've got derivative of 1 over n, which is what? Okay, -1 over n squared. So we can come back over here. Equals limit as n goes to infinity. And here we've got -2 over n squared minus 1, and then divided by -1 over n squared, which, running out of room there, limit as n goes to infinity, and we can make this, we can cancel out those negatives, right? And this is 2 over n squared minus 1 times n squared, right? And so then this will become limit as n goes to infinity, 2n squared over 2n squared minus 1. And then if we go ahead and we can now take the limit there, right? When we're going out to infinity, it's essentially, oh, wait. Why did I add that 2? Oops, that 2 shouldn't be there. Sorry. Is that what you were about to say? I caught it. And so this is going to be, because I was about to say it shouldn't be 1. So this will be 2 over 1, the ratio of our leading exponents, right? Or leading coefficients. So 2. Right? And then, therefore, f of n times natural log of n plus 1 over n minus 1 goes to f of 2. And therefore, a sub n goes to e squared.